Welcome to this web lecture on the network design problem. This is actually the first of two web lectures. So in this web lecture, we're going to talk about the mathematical model formulation for the network design problem. And in a second video, we're going to look into the so-called drop heuristic, which is going to help us to efficiently solve these kind of problems. The problem that we're going to look at throughout both of these videos is transporting water. Historically, this was done with aqueducts, but these days this of course happens through a network of pipes. And this is exactly also what Brabant Water is using. So Brabant Water is the company that ensures that all households in the province of Brabant in the south of the Netherlands have a steady supply of fresh drinking water, but also that ensures that the wastewater leaves the house and is being transported to sewage water treatment plants before they're being reintegrated into the water streams. And the problem that Brabant Water might now face is that Brabant Water must connect all households by a network of pipes. And the backbone of their network consists of a freshwater spring, denoted by F, and two sewage treatment plants, denoted by S1 and S2, which all have a capacity. And then they also have to satisfy the demand of 5 cities, Breda, Den Bosch, Eindhoven, Helmond, and Tilburg, which also have associated demand. Each of the pipes can transport at most 40 liters per second. So if we look at this problem, let's think about how we can formulate this. So what we would like is to formulate the problem in which Brabant Water brings sufficient fresh water into the households in all 5 cities. So at this point, we're ignoring the fact that this water eventually also has to move from the households to the sewage water treatment plants. So what we're doing, if we have any sort of mathematical formulation or the necessity of a mathematical formulation, is we're looking into the recipe for formulations, which means we're identifying sets and parameters, introducing decision variables, and formulating constraints and objective function. In this case, this mathematical model is rather similar to a minimum cost flow formulation, so we're using this as a starting point. So what we're having in a network design problem is we're having locations, which is origins, destinations, and potentially also intermediate nodes. We have a parameters, which is our capacities, supplies, demands, and costs. And we have decision variables, which refer to the flow between 2 nodes. Now, if we want to extend this to a network design problem from a network flow problem, we have to include costs for opening an arc. And this cost for opening an arc is denoted by Fij, so it's a fixed cost. And of course, we also need to associate this opening costs with a decision variable which tells us if we're actually opening an arc, yes or no. And this is denoted by Yij. So Yij is 1 if we build a pipe from I to J. And then we have a lot of constraints. So we have to adhere to the R capacity, we have to meet supply and demand, we have flow balance, and we have non-negativity of the decision variables. And we don't have to change that much here. We just have to ensure that the arc capacity is 0 or the flow is 0 if an arc is not open. And we can do this quite simply by multiplying the right-hand side of this first constraint with the decision variable y, which means that we're adhering to arc capacity and we're satisfying flow. And lastly, we have to change the non-negativity of the decision variables to the domain restriction because we also have to ensure that y is either 0 or 1. If we look into the objective function, right now we only have the variable costs in here, but we of course also have to add the fixed costs. And in this case, the fixed costs have to be multiplied with the opening, and this is exactly what we add here in the objective function. So now we have this mathematical model formulation, and we can parameterize this both for fresh and for sewage water treatment. So the fresh water obviously goes from the spring to the households, and the sewage water goes from the households to the sewage water treatment plants. And both cases we can parameterize. And this is the first thing that I would like you to do. So I would like you to determine the values of these parameters that we're having, so of U, of C, of F, etc. And that separately for fresh and for sewage water. Secondly, I would like you to extend the formulation that we saw on the previous slide to multiple commodities, i.e. that we're able to jointly transport fresh and sewage water. What I would like you to keep in mind is that might not actually make sense. And this is a general thing. Even though we can formulate something, something still might not really make sense. And this is a very clear case of that. So what we're looking at next is why a multi-commodity formulation really doesn't make sense in this example. So let's just say our multi-commodity network flow formulation tells us to open these arcs in here. And now we're trying to assign both the fresh and the sewage water to these pipes. So we're starting with fresh water, and we're using these 5 arcs to get the fresh water from the freshwater spring to all locations. And this also works with capacities and everything, that is fine. But now the problem is, if we now want to add sewage water, that is reasonably simple for Den Bosch, for Eindhoven, for Tilburg and for Breda, because we can just use those direct connections. But it is extremely difficult for Helmond, because Helmond, the only way we can reach either S1 or S2 is to go via Eindhoven, which of course means if we now use sewage water in the same pipe as fresh water, that the water that reaches Eindhoven is actually no longer clean. So even though we can formulate things, sometimes we have to think a little bit further, and we have to make an argument why a formulation in a given application doesn't make sense. And this is something that I would like you to really take away. Think before you model. Think, what is it that I actually want? What might be negative effects of using a standard formulation here? Of course, it is possible to now provide a formulation in which each pipe is used for either fresh or for wastewater, which is not too much of an extension of the multi-commodity network network design formulation, but it is slightly different. And from these points, what I would like you to take away about the network design problem is, first of all, the problem formulation. Secondly, I would really like you to take away that sometimes it is good to argue that a formulation does not make sense. What I would like you to do is parametrize the example both for fresh and for sewage water. I would like you to formulate the multi-commodity network design problem, both in the wrong and in the right way. And what we're looking at in our next web lecture is the drop heuristic. Thank you very much.